Welcome, my dear students, to Chapter 6's coverage of the electronic structure of atoms. To begin, I would like to share with you a fun fact. Did you know that fusion reactions of helium-3, which is the isotope of helium that has only one neutron instead of two, have the potential of creating large amounts of clean energy? It's true. Unfortunately, there are only about 30 kilograms of helium-3 on Earth. However, there are about 1 million tons of helium-3 on the moon. Gerald Kolsinski, a professor of the University of Wisconsin, is researching helium-3 energy, which you can see in this link right here, which I've also included in the description below. This takes us beautifully to Chemistry Cats of the Day. The first one says, teach us about absolute zero. Okay. And the second one says, what did the bartender say when oxygen, hydrogen, sulfur, sodium, and phosphorus walked into his bar? Oh, snap! Ha ha! Ha! Dad joke. Okay, so after this video and a series of other videos, it will follow, and they'll all be linked to each other in the descriptions below or somewhere in thumbnails and so forth. You should gain the following skills: being able to describe frequency and wavelength using equation 6.1 from our text. If given a frequency or a wavelength, use figure 6.4 to identify its radiation type. Explain quantization of energy and use equation 6.2. Use equation 6.8 and be familiar with the Heisenberg uncertainty principle. Be familiar with the 4 types of orbitals, sps, ds, and fs, and note that we will skip section 6.3. So that's where we're going to go. Let's launch into it. Starting with electromagnetic radiation. So as it turns out, electromagnetic radiation is a fancy term for light, or radiant energy. There are 7 different kinds of electromagnetic, or EM, radiation that we know of at least. Visible light, which is EM radiation that we can see, is just one of them. Here's a diagram showing all of them, which I've taken from our textbook. And if you want to know what book that is, just check the description below. So EM radiation behaves kind of like a wave. What does this mean? Well, if you look at a water wave, and this is a very idealized, perfect water wave where it's completely repeating with the exact same shape, so it's a little bit of a fantasy, but the point is, if you look at a water wave like this, you can kind of see that it has a repeating pattern. We have the crest or top of each wave, and then a valley or trough in between. The distance from the top of one wave to the top of the next wave is called the wavelength. The length between waves. So, like a water wave, EM radiations emanate in a wave-like pattern like this. Whoa, 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 whoa. And as I just foreshadowed, the distance from the top of one peak to the top of the next peak is called the radiation's wavelength, for which we use this Greek symbol, which is called lambda. Now, the number of waves that pass a given point in 1 second is called that radiation's frequency, abbreviated by this symbol, which is the Greek letter nu. For example, let's imagine you have a type of radiation that has shorter wavelengths like these. Then let's say that you put a counter somewhere where you were countering as these wavelengths are emanating through space, how many full complete waves go across that point in a second. You can imagine that with shorter wavelengths, there will be more wavelengths crossing that point in a second than if you have longer wavelengths. We see then that as wavelength goes up, its frequency, which is the amount of wavelengths that pass a point per second, goes down. This, by the way, hopefully explains the strange units for frequency, which are inverse seconds or per seconds. Now, as it turns out, all types of EM radiation travel at the same speed, which is the speed of light, c, which happens to be equal to this value right here. Now this means that we can mathematically interrelate wavelength and frequency by using this equation 6.1 from our text. This of course brings us to some beautiful chapter problems. What is the frequency of a radiation that has a wavelength of 20 micrometers? What is the wavelength of radiation that has a frequency of this number right here? And would the radiations in these 2 questions be visible to the human eye? And then lastly, what distance does electromagnetic radiation travel in 150 nanoseconds? Now I will post floating over my head or in the description below access to some videos in which I solve 1 or more of these. I don't really know. In any event, that's the end of this video. Please have an enjoyable rest of your day.